So those are sort of the updates on class. So let's get started on section 2.4. Once I get things organized, here we go. Okay. Okay, so section 2.4, the derivative. So the derivative is sort of our second main thing in calculus. So we started with limits, and limits are going to give us this next thing called a derivative. So before getting to what a derivative is, it's going to take us a little bit. Derivative relies on the concept of slope, which is one of the first things we learn in Algebra 1. So I know you all know about slope, but I just wanted to sort of talk about what slope is representing in application situations. So we all know y equals mx plus b. So for example, if we have a line that is representing snowfall, these are not going to be super accurate pictures, but we might be able to graph the number of inches. Nope, sorry. The number of inches that accumulate over so many hours. And so if it's snowing at a consistent rate for several hours, the inches will accumulate consistently over those hours. So in this case, our slope would be a rate. So this would be the rate of snowfall would be in inches per hour. That's what our slope would be telling us. If we are producing something, like you have a company and you're making coffee makers, for example, you probably have, you will have some costs. So you'll have to spend so much money in order to produce your coffee makers or whatever you're making. In this case, you probably have some setup costs, so you probably won't be starting at 0, and then your costs would increase based on how many coffee makers you're making. So again, we have a slope to this function for production cost. And in this case, our slope would be in the units of dollars per, I'm just going to say unit per coffee maker. So every coffee maker we produce, we'll have to add a certain amount of cost to our production costs. We can also, of course, have negative slope. So if you, for example, if you have so much money in your bank account and you...
Sorry.
Yes.
That dollar over unit, that's also considered a rate?
Yes, exactly.
Okay.
That would be a rate as well. So that would be what our slope, the units of our slope in that situation. And in the situation where you, in a situation where you spend the exact same money every single day, we would also have a line to show like our bank account, the amount in our bank account. So that might be the dollars that we have per day, maybe. So we're spending money at some dollar per day rate. So slope, really, if we think about it in any context of an application that's not just y equals mx plus b, it's always some rate of change. And it's the rate of change of y with respect to x, whatever our y and x are. So if we're looking at the rate at which snow is falling, we could say it's falling 2 inches per hour. If we're looking at the cost that it produces, the cost it takes to produce coffee makers, we could say it costs $20 per coffee maker, just sort of throwing that out there. Or if we're spending money every day, our slope would be the amount of money we're losing, negative $10 per day or something like that. So slope always gives us a rate of change of whatever our y is with respect to whatever our x is. So that is sort of our review of slope. The problem here is that as we're looking at these three things, it's not always constant. Snow is not going to be coming down at the exact same rate for a very long time. We generally don't spend the exact same amount of money every single day. So this idea of slope is really important, but it's not always practical when we're looking at things that change at different rates depending on the situation. So that's what the derivative is going to do for us. It will still be talking about this idea of slope or rate of change, but it will be for things that are not necessarily straight lines that can be moving up and down, or just up or just down, but not necessarily at a consistent rate. So it's going to take us a few steps to get there, but that's where we're going. We're going to be talking about rates of change for things that aren't just linear. So we're first going to talk about average rate of change. So here is our first example. I'll give you a moment to go through this first. Okay, so we have a small steel ball that's dropped from a tower, and it's going to fall a distance of y feet in x seconds. And that will be approximately modeled by this formula y equals 16x squared, or f of x. A lot of times in our book, they'll use y equals f of x equals the function, just to show that we could represent it with y or f of x, but we don't really need both of them. So this is a physics equation. So when something falls from anywhere, it's accelerated by gravity. So it's going to speed up as it falls. So the speed of this ball as it falls is going to change over time. So our first question is that we want to find the average velocity from 2 seconds to 3 seconds. So if we want to know the average speed or average velocity that this thing is falling, we have to sort of remember this distance equals rate times time formula. To define the rate or the speed or velocity, we would divide distance over time. So we need to know the distance that this ball is moving over the amount of time that it goes to find the average speed. We know that the time is 1 second because it's traveling from 2 seconds to 3 seconds. How are we going to find the distance that it traveled?
Are we going to do, I guess, replace the x with 2 and then the x with 3 and then add them and divide them by 2 to get the average?
I think square root of 16.
So we do want to plug in the 2 and the 3. We don't need to take the square root because we're not going to need to solve for x. We're just finding the y's. So our distance would be the distance that the ball is traveling between 2 seconds and 3 seconds.
Does the top equation have anything to do with A?
Yes.
Okay.
So would the answer be 80 then? Like, would we subtract the 2 answers if we're not doing the average?
We will subtract them, and I haven't done it yet, so we'll find out if it is 80. I don't have the solution in front of me. But yes, so basically our average velocity is going to be the distance that the ball travels in 3 seconds minus the distance it traveled in 2 seconds. And actually I'm going to erase this 1 for a second just to show what we're doing with this. Divided by the 3 minus 2. So we can't do any adding together and dividing by 2 here, because I see where you're going with finding the average in that way. But we could only do that if we knew the 2 velocities. Here, we don't know how fast the ball is going ever. So we find the average velocity by finding the distance it traveled completely over the time that it's traveling. So just a little side note from this particular example, if it takes you 2 hours to get to Phoenix, and the distance is, I don't actually know what the distance is. The distance is 100 miles. We would know that we're probably speeding up and slowing down throughout that drive, but we could find our average velocity by taking the total distance and dividing it by the time that it took us to travel. So that's what we're doing here. We're looking at the distance that this ball traveled divided by the time that it took. And we will have to use this formula to find f of 3 and f of 2. Which we can do in this whole function. So let's see. So f of 3 is going to be 16 times 3 squared. F of 2 is going to be 16 times 2 squared. On the bottom, just 3 minus 2, which is 1. So we don't really need that. So on top, we have 16 times 9, which is 144, minus 16 times 4, which is 64, and that is 80.
And I'm guessing if we don't include the units, then it's wrong.
Yes, we do need units here. So anytime we're doing any sort of word problem or application, units will be necessary, and we will be seeing more and more of those from now on. So here we're looking for the average velocity. So we can take the distance that we traveled divided by the time it took to travel that distance. And so this is still not exactly, this isn't quite the concept of derivative, but it's going back to this concept of a rate of change. So we're finding the average rate of change, or the average velocity from one point to another in something that's changing its velocity as it moves.
So real quick, if we were to do the average velocity of say like 5 and 6, or let's do 5 and 8, then we would divide the whole thing by 3. All right.
Yes,
Awesome.
exactly. Yeah, and that's actually a good segue into B of this. So building on that idea, our next thing we want to find is the average velocity from x equals 2 seconds to x equals 2 plus h seconds. So here we're sort of starting at the same place. We're still starting at that 2 seconds, but we don't know exactly how many seconds after. We just know it's h seconds. So between 2 seconds and 2 plus h seconds. So how will we figure out the distance that we traveled between 2 seconds and 2 plus h seconds?
Two plus h minus 2.
So that will be
denominator?
yeah, so that'll be the time, because that's the time of the later time minus the earlier time.
Can you go ahead and just reduce that to h?
Yes, we can.
So then the top
the
would
numerator.
be 16 bracket 2 plus h bracket squared minus 16 bracket 2 bracket squared.
Exactly, yes. And I'm going to write that in the function notation first, but that is exactly what we're looking for. So our function is giving us the distance that this ball has traveled in this amount of time, in these number of seconds. So the distance it traveled in 2 plus 8 seconds is 4 of 2 plus h, f of 2 plus h, wow. My mouth and brain are not connected today. The distance that it traveled in 2 plus h seconds is f of 2 plus h, which is that 16 times 2 plus h squared. And then our distance traveled in 2 seconds is the 16 times 2 squared. So we're doing the exact same thing as above. It's just instead of knowing 2 and 3 seconds, we have 2 and 2 plus h seconds. So we can simplify this a little bit.
These are always going to be subtraction on top and bottom, correct?
Yes. Yeah,
Okay.
because we'll always want to know the difference between those two. So simplifying, so we need to FOIL out that 2 plus h. Be super careful. 2 plus h squared is not 4 plus h squared. It's 4 plus 4h plus h squared.
So, okay, never mind. I'm sorry.
Okay, that's fine. So when we distribute that 16 through, the 64s are going to cancel each other out. And woo, we will have 64h plus 16h squared over h, and an h cancels out of each of those. So I went through that simplifying a little bit quickly, but you can do that on your own to verify that this is all correct. So we were able to put in our 2 for our starting time and 2 plus h for the time we're moving. So this little ending formula, 64 plus 16h, would give us the average velocity between 2 seconds and any number of seconds after 2. So h could be anything. It could be 3 seconds after 2, or it could be a half a second. This would give us the average velocity between 2 and any number of seconds after that. So we have an average velocity formula, which is actually what we were just doing, just stated a little more formally, is this, or excuse me, average rate of change, which velocity is just a specific example of that. And this is in the book. Let me find the page. (133). So average rate of change in this could be velocity, like we were just seeing. It could be the cost of making coffee makers, cost per coffee maker, can be anything that's changing. The average rate of change from one starting point to the next, if our starting point is A and we're going up to A plus H, this is our average velocity or average rate of change. And so this is exactly what we were just doing. We plug our ending point into F minus our starting point into F divided by the difference between those in the denominator. And so H will always be the thing in the denominator because our A always gets canceled like it did in the 2 plus H minus 2 up above. So this might look a little familiar. You had some problems like this in your first homework using the plugging x plus h and x into functions like this. So we have our average rate of change. So now we're going to sort of step back into just regular graphs without units for a moment. and talk about secant lines and tangent lines. So we're going to use that average rate of change formula to find the slope of the secant line that goes through x equals 3 and x equals 6 on this function. So this function f of x is what is drawn here on the graph. So the first question before we get too deep into this, what is a secant line? Does anyone know?
It's a line that touches a slope or a function on a graph. Or does it go through? I can't remember.
It goes through. So tangent
It goes through, okay.
is the line that just touches, and we will get to that in a little bit. A secant line goes through at 2 points. So we're looking at the one that goes through at x equals 3, which is right here, and x equals 6. So the secant line would be this line, and that should be straight, but you can pretend it's straight. So this is a secant line. It goes through 2 points on a graph. So I'm going to write that average rate of change formula down here again, just so it's handy. So you'll notice in this context, the average rate of change formula is really just the slope formula between 2 points. We're going to be subtracting the y of 1 point minus the y of another point divided by the x's subtracted. So this is really just the slope formula. Between the points a, f of a, and a plus h, f of a plus h. Probably didn't need that first parenthesis. So I think you're starting to work on this, but just so we're all on the same page, we are being told that A is 3 in this case. What is H?
Six.
Almost. So A is the x that we're starting at. H is the thing that's getting added to A to get to our other point.
Is that 4 or 3?
3. Yeah, because we're
3.
we're starting at 3 and going up to 6. So H is also 3. They're not always going to be the same. It's just
At first I thought it was on the y-axis, but it's based off the x-axis.
so, yep, based on the
X.
Yes. So we're still going to be plugging in f of 6 for the first part because that's a plus h, and f of 3 for the second to find our y values. But then on the bottom, we can just use h is 3, which comes from 6 minus 3.
Equals 1.
What equals 1?
Right. The slope?
Oh, okay. Let's find out. I don't think it's quite 1.
3 over 3. Can
So
you
we're
subtract
plugging-
those? Or
So we cannot subtract the 6 and the 3 that are in the f. So we have to evaluate the function at 6 and evaluate the function at 3, and then subtract those.
okay.
And I would actually recommend we don't have to put it all into the formula at one time. We can sort of on the side find f of 6. So plugging in 6, we get f of 6 is 4. And then we would also have to plug in f of 3.
Did you get a quarter for that one? F of 3?
Yes.
Okay.
And we do have the graph here to sort of confirm that, but normally we won't be using a graph. You'll have to just plug it in and find it. And so we can't be afraid of fractions. So 4 minus 1/4 is 16/4 minus 1/4, which is 15/4.
What is that right above that line that you just wrote on the right side? Is that
Yeah.
9/4?
Yes.
Okay.
From squaring the 3 to get the 9, and then it multiplies with the 4.
Okay.
And would you rather us use fractions versus decimal for this?
Yes.
Okay.
And the reason is that decimals are going to be rounded a lot of the time. And so it's better to use fractions to keep an exact answer. There will be times when we want decimals, but it'll be clear. It'll say round to 2 decimal places or something like that. So all of this is just evaluating f of 6 minus f of 3. So we can do f of 6 and f of 3 independently, and you can use a calculator for this kind of thing, as long as we get an exact answer, which in this case should be 5/4.
And on this, we wouldn't need any units, right? Because there's no units to...
Correct, exactly. Here, we don't have a word problem. It's just a standard XY graph with no context. So we don't need units. So the sort of goal here is to see that that concept of average rate of change graphically is the same as the slope between 2 points on a graph. So the average rate of change between these 2 points is the same as the slope of the line that goes through them. So the average rate of change is really just the slope formula between 2 points, whether it's on a graph or in the context of a dropping ball or anything. So we're going to sort of take this up a notch, and let me get my thing ready. Are there any questions so far about what we're seeing here?
I have a question. How do you, without having a graph, how do you figure out your distance from the 3 to the 6? Like how h equals 3? How do you figure that without looking at the graph?
Oh, just by subtracting 6 minus
Oh.
3.
Because 6 comes from where?
Oh, the 6 came from the problem.
Ah, oh, okay, okay. I got you. Perfect.
Yeah, so we were given those two x values, and so the h just comes from the distance between them.
Gotcha.
So in this case, we're using this average rate of change formula, which gives the slope between these 2 points. So A is fixed, that's our 3. And this formula would give us the average rate of change between 3 and any h that we wanted, so we can change h freely. So we are going to do a little in-class activity. So today's in-class activity is a little different. So if you go to the Canvas page, I guess I should just share this to show you what I'm looking at.
Under module?
Yes, in the week 3 module, if you go to today's class, there is a little thing that says 120 in class activity, and I just published it, so you wouldn't have seen it before. When you click on that, this is a quiz, but it's not really a quiz, it's just a couple questions. At the very top, under the instructions, there is a website to go to. So if we open that link, you will see a graph that looks similar to what I was just drawing. You'll see on the left side, the function that we are just working with is there. That's the same exact f of x. A equals 3, so don't change A for now. Leave A at 3 because that's the A that we were using. And then it has H is 3 as well. H can be moved, and that's what you're going to be doing. Then the fourth line down here is M, whoops, M standing for slope, and you'll notice that this is the average rate of change formula that we were just using, f of a plus h minus f of a over h. So when h is 3, we do get 1.25, which is what we just found, 5 over 4. So there are some questions in this quiz that I want you to take a little bit to do. So question 1, click and drag the green point freely. So we can click this green point and drag it around. It can drag anywhere. It's just going to follow that red parabola. And it asks you to answer some questions. So there are 4 questions. Most of them you don't need all of this space. You can write one word or just one number. And if you're not quite sure, that's okay. We're going to sort of go over this together, but I want you to explore this thing first. And just one note is that the word tangent line came up earlier. A tangent is a line that touches a graph at just one point. So this purple line is the tangent. This green line is the secant. So take a little bit on your own to start to go through those questions and the graph. If you're unsure, you can ask me, but we're going to go over these together in a little bit.
For whatever reason, I'm able to pull up the Desmos graph, but the questions, I can't open that. And the Desmos is actually open in my Canvas, and it keeps like refreshing almost, like coming up, and then I move off the screen, and then I'll restart. I've never really used my Canvas for anything else. It's kind of weird. It usually opens like in a separate window.
That is strange. So you can't see any of the questions that are there.
No, and my Desmos keeps like, I'm gonna see if I could open it up in a different window because it just keeps like flashing basically. I just keep thinking Desmos, and then I'll see the graph up 3 seconds, and I'll go back away and reload and reload. It's just like Canvas being weird, I think. And I can't. Okay, I got it. Awesome.
Wonderful.
Yeah.
So, Madeline, I had a quick question for you.
Yes.
On the survey, I do have Desmos open, and the survey, when we're done with this, do I just press submit the quiz? That's it?
Yes.
Simple enough? Okay,
Exactly.
gotcha.
Yep.
I didn't know if this would kick me out of Desmos. Okay, bad, awesome. All
No,
right.
yeah, you should still have Desmos up. And if you finish, we'll go over this in a few minutes together, but if you finish early, you can just take a little breather.
Madeline, what was the original value of A? Was it 3?
3, yeah.
Okay. Is it possible for you to explain question 1 in a different way?
Yes, let me look at it so I can remember how I explained it the first time. Okay, so clicking in, you're just like moving the green point around in any way. And so the green point, it can get closer or farther away from that purple point. So the purple point is at A, at x equals 3. So we can see that as the green point moves, the slope of the secant line is changing since it's a different point. So as you move the green point, we can see that the secant line is getting closer or farther away from the tangent line. And so I just want you to compare the slopes of the secant and tangent lines in relation to if you move the green point farther from the purple point or closer to the purple point.
Thank you.
It's not like a super technical question, so I'm not looking for anything exact, really. So in about 2 more minutes, we'll go over this together. So even if you're not quite finished by then, that's okay, but about 2 minutes. Okay, so let's look at these together. And if you're not quite finished, you can just sort of be filling it out as we go over these questions. I'm not going to be grading on your exact answers. I just want to see that you were answering the questions and participating. So here is our graph. And so the first question was, if we move this green point around, what is the relationship between the slope of the secant and tangent in relation to how close or far the green point is to the purple point?
So
The value
I
of
said,
H.
I actually didn't hear. I think, Deanna, were you gonna say something? Or someone? I heard something. I heard
Value
voices.
of H.
So what about the value of H?
It's changing
Yes.
based on where it is on the parabola.
So the value of H is representing how far or how close that green point is to our purple point. So how does that changing value of H change how close the slope of our green line is to the slope of our purple line?
I just said that the closer the secant point gets to the tangent point, the more similar their slopes become.
Yeah, exactly. So if our green point is super far away, their slopes are not very close. But if we drag our green point closer to the purple point and H gets smaller, that is key, then their slopes are getting closer and closer together. So that's kind of what I wanted you to see, even if it wasn't exactly easy to word. Just noticing that if the point is far away, the slopes are super different. If the point is close, their slopes are much more similar. So the next question was, what is the value of h when the secant lies exactly on top of the tangent line. So what value of h gives us the same line here?
Zero,
It's
but it's undefined.
Yes, so when h is 0, there we go, I got it on there. When h is 0, the secant line is exactly where the tangent line is. So that's basically saying when we were doing our average rate of change, if we're going from a to a plus h, there's some distance in between them. But if they're the exact same point, then we're not adding anything. So h is just 0. And that was the part of the next question. Whoops. Or was it? Oh yeah. So the fourth item on the graph gives a slope. And so the question was, when these two are the same, what does the formula say the slope is? And yeah, it was undefined. So when we have h is 0, it says that the slope is undefined. But our fourth question was, does your answer in question 3, undefined, match what you would estimate the slope to be on your graph? So does this look like an undefined slope?
No.
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 Yeah, okay. No, it doesn't. So undefined slope is actually supposed to be a vertical line. This is definitely not undefined. We can see that there is some rise and run here. So that undefined comes from the h being 0. So if we're looking at our average rate of change formula, this doesn't work when h is 0 because we can't just be throwing an h in the denominator or a 0 in the denominator because we get something undefined. So this difference is where our calculus comes in. If we know, oops, I'm dragging too many things at once. Change that back to 3. So if we know how to find the average rate of change, and we want to know, let me rephrase that. If we know how to find the slope of the secant line, but we want to know the slope of the tangent line, we can think of it as, well, it's the average rate of change when h is 0. The problem is we can't just plug 0 in because then we get undefined. So we get to use our previous knowledge of calculus to think, when we get this point closer and closer and closer and closer to the other point, the slopes are getting closer and closer together.
The limit.
The limit, exactly.
So
So instead of plugging in h, we can find the limit as h gets closer to 0, and that can tell us what our tangent slope is going to be. So this is, when we started out, I was talking about how we want to have a concept of slope for things that change, that aren't necessarily lines. And this is our concept of slope for something that curves. So if we have a curving thing like this parabola, we can talk about the slope at this particular point if we know what the slope of the tangent line is. So the slope of the line that touches just at that point will be our rate of change at that. So let's go back here. We've been talking about, nope, that was frozen. So we've been talking about average rate of change and the slope between secant lines. But what we want to know is about instantaneous rate of change. So rate of change at one very instant, not over some stretch of time. And this is that limit. So wait, let me move this example out of the way for a minute. So instantaneous rate of change is that exact same formula. So this is the average rate of change formula. It's just that we're taking that h and making it closer and closer and closer to 0. So we're taking the limit as our h gets closer to 0. The limit as that green dot gets closer to the purple dot. And this is in the book as well, on page 135. So this is where we're going. We still haven't exactly defined derivative yet, but this is sort of the key part. We don't want to know the slope over 2 different points or the average rate of change over 2 different points or times or whatever. We want to know the rate of change at an exact instant. So there's no change in time whatsoever. And so we're taking that average rate of change formula and then taking the limit as h goes to 0. So this is a continuation of our steel ball example. And so this is just that same context, so you don't have to write it down again if you have it in your notes. The steel ball is dropped, and we have the formula for the distance that it traveled. Our last bit of that question is that we want to know the instantaneous velocity when x equals 2. We already did most of the work here. So I'm going to say, so we want to know, so instantaneous velocity is just one example of instantaneous rate of change. So it is going to be this formula where we have f of 2 plus h minus f of 2 over h. But we already found this whole thing in our previous example, other than the limit. So in our previous example, I'm going to go back to that for a moment. We found the average rate of change from 2 to 2 plus h. And we found that it was 64 plus 16h. So we can actually just use that here. Since it's the same problem, we already did the work to find that average rate of change. So this is from part B. And how do we find this limit as h goes to 0?
Plug it into decimals.
Nope.
Plug in 0 for h.
Yes, exactly. Here we can just plug in 0 for h. So this is one of those situations in those first limits we were doing where nothing bad happens when we plug 0 in. That's not a 0 in a denominator or anything. So we can just plug in 0 for h and we get 64 feet per second.
How do you tell when you plug your limit into the equation versus if you have to calculate something? How do you tell when you're supposed to do what?
So plugging in is like the first try. If we can just plug in the number and we don't get anything undefined or undetermined, then we can just plug it in.
And the
oh,
only
sorry.
thing that would be undefined would be a 0 in the denominator, right?
Right.
Okay. I'm sorry, go ahead.
No, not at all. So most of the problems, all of the problems in this section will have really nice limits where we should be able to just plug it in right away. I also want to just make a little note. This says if the limit exists, we are not going to be worrying about things where the limit doesn't exist, but we should always have nice limits here. It'll never be like an infinity or a DNE or anything like that. We'll be able to plug it in and get a number. So this is the instantaneous velocity. So when that ball is dropped at exactly 2 seconds, it is traveling 64 feet per second. So if we were able to just like take a screenshot of time at that moment and get its velocity, it would be traveling 64 feet per second. So this is the derivative. This is a specific example of a derivative. The technical definition of derivative is here, and this is on page 138 of the book. This is the same definition, but we're using x instead of a. And I'm going to explain what this notation means and how to read it in a moment, but I'll give you a moment to take this in. So we have a function f of x. We define the derivative of f at x. It's denoted. So this thing, that little mark is not an apostrophe. It is prime. So this is read f prime of x. Prime. So prime, which really is just an apostrophe, but we don't call it that. That little mark means we're taking the derivative. And so it is denoted, so f prime of x equals the limit as h goes to 0 of that same average rate of change formula. But now instead of using a, we're using x, because the derivative applies to any x value on the function.
So will we see where we have to use a and we have to use x, or is it all changed over to x now?
So pretty much changed over to x now, because we can always plug in anything for x. So we could have been plugging in like 2 for x as it was in a before.
Okay.
But yeah, use x. So there's a few important things about the derivative, and we'll, as we do more work and more applications with derivatives, it'll be a little more clear what this actually is. But there's a couple different interpretations of derivative, and we've seen both of these already today. So one way to think of it is the slope of the tangent line at any point on the function. So the derivative at some point on the function is the slope of the tangent at that function, or at that point on the function. We can also think of it as the instantaneous rate of change at any x value. So like when the ball is dropping, we found the instantaneous velocity, which is a rate of change at a certain time. So these are both basically the same thing. They're just kind of different ways of looking at the same thing. In either way, we're looking at how y changes as x changes at one exact point.
Can we use abbreviations?
Oh.
Can we use abbreviations for, I don't know. Well, actually, there's no labeling. Never mind. Don't mind me.
Okay. The other important thing about derivative, which we'll see when we do a couple examples, is the derivative is itself a function. So when we did the instantaneous velocity b just now, we were doing it for one specific x value, but we can find just the general derivative without plugging in an x, and then the derivative is itself a function as well. So f prime of x is its own function. So most of the time we will be taking a derivative as a function, and then we can use that to plug in x values if we want to know instantaneous rates of change at certain times. So we can use it as a function just like we would a normal function. So let's do an example of finding a derivative using this definition. So the book gives a 4-step process for finding the derivative, which is really just a way to build this limit without doing it all at once. So this formula can get kind of nasty depending on the particular function. And so we can break it up into steps. You are not required to write out or to use the exact 4-step process, but I encourage it because it makes it easier to put this limit together. And it is on page 139, and we're going to go through the steps now. So I just put the definition of derivative up here again, just so it's handy. But that's the same thing as was on the previous page. So our job is to find the derivative of this function, 3x squared plus 1. So the first step is to find f of x plus h. So that's just the first part of that limit. And this is something similar to what you did in the review assignment, just to practice. Plugging things into functions. And so we do want to multiply this out and simplify it. So be really careful to FOIL out that x plus h squared, and then we'll distribute the 3. So this is our f of x plus h. So our second step is finding f of x plus h minus f of x. So that's just the numerator on this derivative. So we know what f of x plus h is. We just found that. Did I put a cube there? I did. That should definitely be a square. Sorry about that. Be super careful here. One thing that I saw a lot on homework 1 was mistakes with minus signs when we're subtracting a whole function. So we're subtracting this whole 3x squared plus 1, which means that we need parentheses there to show that that whole there we go. The whole 3x is being subtracted and the 1 is being subtracted. So this is something I saw a lot on homework 1, is forgetting to distribute that minus sign into the function that we're subtracting. And that will really throw things off and it'll make our limit impossible to take. So be sure to do that, so distribute that minus sign. And we'll notice that at this stage, at the f of x plus h minus f of x stage, a lot is going to cancel out. So this 3x squared and the minus 3x squared cancel, and the 1 and the minus 1 also cancel. So it's normal that a lot goes away there. And we end up with 6xh plus 3h squared. So then our step 3 is to put that, what we found in step 2, divided by h. So we have f of x plus h minus f of x over h. We just found that that whole numerator is 6xh plus 3h squared. So the point of these steps is to build on each other. So we can use what we did in the previous step to plug into our next step. And here something great happens, h's cancel. So we have the h in the denominator cancels with one of the h's in each of those terms. And we end up with 6x plus 3h. So these first 3 steps are really just that average rate of change formula with x instead of a. And in step 4, we have the limit. And just a little note, depending on the format of the typing, sometimes the h going to 0 is off to the side like this. It doesn't mean anything different. It's just how formatting occurs sometimes. So this is still limit as h goes to 0 of, and that whole thing was just 6x plus 3h. So this part, I think, sometimes yes, exactly. And I think this sometimes throws people off because we have an x and an h here, but we have to just note that we're only taking h to 0, the limit as h goes to 0, so the x is just staying as it is.
I almost did that.
Yeah, it's easy to do. But so that, yeah, which variable is going to 0 is really important, and it'll always be h for these. And
So is that
now
our
we just
complete
have
answer?
x. That is it. Yep. So our answer is, if we're going to write it in proper notation, which we should, is that f prime of x equals 6x. So that's saying the derivative of f is 6x.
If we were to do one of these problems in the homework, do you want us to do the step by step, or could we just skip all the way down to the final step and fill it all in?
You can skip all the way down to the final step and fill it in, or it just goes to here. However, I think it's easier to do it step by step, because you're going to have to do all of this anyway, and putting it all together at once means you have a kind of a mess to get through
Understand.
at once. So you don't have to go through steps, but I recommend them to lessen the possibility of like little mistakes with adding and minus signs
no
and
problem.
things like that. So this is on the previous page when I mentioned that a derivative is itself a function. This is what I mean. Our answer here is that the derivative is 6x. So this function would give us the instantaneous rate of change, or the slope, at any x value that we wanted to know about. So it's like a function that tells us about the rate of change of the original function.
What would we
So
use
when
this
we're
for?
finding,
Sorry, what would we use this for in like a different, like in an everyday real world?
so everyday real world would be like if we, so in next week in section 2.7, we're going to do some business applications. So this would be like if we want to know how much profit is increasing or decreasing depending on how many units we're producing. We can use the derivative to tell us the rate of change of profit per unit based on how many units we are producing. So if this was like profit is modeled by this function, this would tell us how much our profit is increasing depending on how many units we're producing.
Gotcha. So it makes more sense to have the like labels and the units of measure than it to make a real world experience out of it. Okay.
Yes. Yeah, and really calculus, basically anything that ever changes can be, the derivative can be applied to it. We won't get super complicated in this class, but things like weather are modeled based on derivatives because any sort of change in one thing affects changes in other things. So all sort of dynamic things that change and affect other things use this idea of a derivative because it's so focused on how quickly or slowly things change in relation to one another.
Gotcha. Thank you. That makes a lot more sense now.
Good. Yeah, so it feels kind of abstract when we see it this way, but we'll do lots of applications. Before that, though, for our last bit today, I want to do one more example that's a little more complicated, or just a little more algebra heavy. This one was a polynomial, which are usually pretty nice to work out. I want to do one where we have a rational expression. So same exact question. We want to find the derivative, same limit, and we'll do the same steps. So here our function is f of x equals 1 over x. So plugging in our x plus h, we have 1 over x plus h. So not too much to do there. Step 2 is where we have to be careful. So if we want to know f of x plus h minus f of x, this is 1 over x plus h minus 1 over x. And we want to simplify this. So algebra skills are super important here.
Can you pull up
But we
real
need-
quick?
Yes.
Thank you. Okay.
So we have two fractions that have different denominators that we need to subtract. So we need a common denominator here. What is our common denominator between 1 over h and 1 over x plus h and 1 over x?
Isn't it x times x plus h?
Yes, exactly. X times x plus h. We can just multiply those two denominators together. So if we need to change our two fractions so that they have that common denominator, the 1 over x plus h will just multiply by x on top and bottom. And we get x in the numerator. The 1 over x we have to multiply by x plus h on the top and bottom. So remembering some algebra, if we have rational expressions that have different denominators, we need a common denominator. And often that will just be the two denominators multiplied together. So this will turn into x plus h minus x plus h over x plus h. And here we have to be super careful again. So we're subtracting the numerators of these two since they have the same denominator now. We can just subtract the numerators, but we have to be careful that that whole x plus h on top is subtracting. Which gives us so do be careful with that minus sign. We're subtracting fractions, so that minus is applying to the x and the h in the parentheses. The x's cancel and we're left with just minus h in the numerator. So when we have rational expressions, that step 2 can be a little bit tricky if we don't remember our algebra well. So our third step is our f of x plus h minus f of x, which is the thing we just found in step 2. And that's being divided by h. So we have a fraction divided by h. So if we look at this step by step, really what's happening here is that we're dividing the top by h, which we can look at as multiplying by the reciprocal. So at this point where we have our fraction in the numerator dividing by h, we can think of it as flipping and multiplying by 1 over h. And the h's cancel, which is great. We should be looking for h's canceling in these problems. Just don't forget that that negative is still there. So now we have a negative 1 over x times x plus h.
If the h's don't cancel at the end,
I heard if, oh,
sorry, if the h's don't cancel at the end, does it mean we did something wrong in the previous steps?
Probably, yes. Definitely, yes. So, and the reason for that is that when we get to step 4, you should be able to take the limit without having something undefined. And so that h that's in the denominator of that step 3 has to cancel in order for us to plug in that 0. So the
Okay.
h's will cancel.
Thank you.
Because when we get to this point, yeah, when we get to this point, we can take that limit as h goes to 0 of the thing that we just found. So we have negative 1 over x plus h. So there is an h in the denominator, but it's not an h that's going to make the whole denominator 0. So in this case, we can plug in that 0. Nothing bad happens. It's not an asymptote or undefined or a hole or anything. It just turns out to be x times x.
And earlier in the equation, on step 2, was there a reason why you kept it as negative h over x times x plus h, and you didn't do that? You didn't simplify the x times x plus h? Was that so you were saving that bottom h for the last step, or how would we know to not do that?
You mean not doing?
Yes. Yep. Exactly.
I didn't do it just because it wasn't necessary. It wouldn't hurt it if we did. We would get the same outcome either way.
Okay. Understandable, yeah, because it would be 0. Yep.
Yeah, so that second term would turn out to be a 0.
I spent a good chunk of time sitting and staring at the same thing and going, she's not doing it, don't do it, just wait and see.
Right.
Yeah. No, but yeah, it won't hurt anything. In general, I don't multiply out denominators if it's not necessary, just because something might cancel at some point. And so having it in factored form is handy, but it doesn't matter in this case.
Can you go back to step 4? Sorry.
Yes. Oh, no, you're fine.
Thank you.
I actually was going to write that last line anyway. So our derivative of f is negative 1 over x squared in this case.
Why do we call derivatives primes?
That is a good question, and I don't have the answer to it. Well, we can talk about this now. There's actually a few notations to use for derivatives. And this is just the first one that we introduce. And I believe this is Newton's notation. There are two mathematicians, well, Newton did other things, but two people sort of discovered calculus around the same time, Newton and Leibniz. And the prime notation, I believe, was Newton's notation. And I can't say exactly why he decided to do that. And we can also use prime on a y. If we're not using f notation, we can use it on a y as well. The other notation, which we'll be using more next week, just do this, is this notation, which is very useful in different contexts, and we will see it more later in the term as well. And this is that D basically stands not for derivative, but that's how I think of it. And this is Leibniz's notation.
Is the D stands for delta, maybe?
Yes, it does. You're right. It's an infinitely small delta, a change. Leibniz's notation. And this notation is nice because it clearly tells us what is changing in relation to what. So this is sort of like our slope notation. It's a change in the y divided by the change in the x. So it tells us what our function is divided by what we're taking the derivative with respect to, which is important when we have multiple variables, which we will at the end of this term.
So basically, we'll see all of those notations when it comes to derivatives?
Yes.
Okay.
Yeah. So we're starting out with the prime, that's sort of the usual beginning notation, and it's often used in applications, like when I mentioned profit earlier, when we're doing the change in profit, we usually use a prime. So we'll see all of these notations. I'll bring these up again on Tuesday. But prime is used a lot in math to kind of denote something that is similar to something else or comes from something else, but is a different version of it. So we're sort of starting with our regular function and then doing the derivative. So it's coming from there, but is not exactly the same. So on Tuesday, we are going to do section 2.5, and we will have shortcuts on doing derivatives at that point. But for section 2.4 and your homework for section 2.4, you do need to use this method. So even if you're thinking, I know of a shorter way to do that, we need to use this limit definition to start with. And then next week, we'll find a shorter way to do these derivatives. So that is all for today. I'll post the rest of the homework from this section in a little bit. And I will see you on Tuesday.
Perfect. Thank you. Have a great day.
You too.
Thanks. Bye-bye.
Weekend.
You too.
Yeah,
Thanks for your
that's-
time, Madeline. Have a good weekend.
Yeah, you too.
Thank you.
Have a good day. What's Lagrange?
The notation rather than Newton. I think anyway. I mean, I'm pretty new to this stuff.
I am not sure about that. I mean, I know that Newton was the other discoverer of calculus, but I can't say whether this was his notation.
All right, no worries.
I'm going to look it up.